Here we're going to talk about Half-Life. And Half-Life is a pretty sweet video game if you've ever played it. But Half-Life in this case is the length of time it takes for a material to decay in half. And so what that means is if you have some amount of something, the half-life is basically how long it takes for half of it to disappear. So oftentimes they'll talk about half-life with carbon-14 dating. And carbon-14 has a half-life of 5,730 years, as mentioned here. And then it says, if a specimen had 248 grams of carbon-14 17,190 years ago, how much carbon-14 should be remaining today? So let's look at it just from, kind of a guess and check method, I guess. And then we'll talk about how can we do this as a formula. So let's say they started out with 248 grams. And then 5,730 years later, they end up with half of what's remaining. So I picked some easy numbers to take half of. Half of 248 is 124. And then another 5,730 years have elapsed. 5,730 years. And what's remaining? Well, half of that. And so half of that is 62. So far, we have 5,730 plus 5,730. That's 11,460 if I'm doing my math right. And then, excuse me, another 5,730 years have elapsed. And it's in half again. So that would be 31 grams. So let's see, what's 5,730 times 3? Let's grab a calculator here. 5,730 times 3. Well, conveniently enough, it's 17,190. So, excuse me. So this was 3 half-lives, basically. So after 17,190 years, there will be 31 grams remaining. Well, the way we're going to think about this is one half-life. This is another half-life. And this is a third half-life. So the way we typically will say is we'll say, well, 248 times a half times a half times a half. That was 3 half-lives, and that gave us 31. So a more concise mathematical way of writing it is 248 times 1/2 to the third power. And so this is going to be kind of our general formula for half-life. We typically use the letter A to signify how much you end up with. And so let's talk about what do each of these things represent. Well, the 248 was the starting value. 1/2 is just 1/2. It's half of it. And 3, how did we get 3? Well, that was 17,190 divided by 5,000, what was it, 370 or 730? I forget. 730. So that exponent is how many half-lives? How many half-lives? And that's a word, or it's a phrase at least in math. So how many half-lives was that? The way to figure that out is you take the total number of years divided by how long a half-life might be. Some half-lives are in terms of minutes, and some are in terms of days or hours. So it's not always going to be years on the bottom. It's going to be how long a half-life is. So if you're talking about something having a half-life of 10 minutes, and they're saying, well, what if it was 50 minutes have elapsed? Well, you do 50 divided by 10. If they said 3 days have elapsed, then you would figure out how many minutes that would be. Obviously, there would be pretty much nothing left if it's half-life every 10 minutes. Okay, so let's talk about general formula here. We basically came up with this. A is how much you end with. N sub 0, typically whenever you see a sub 0 like that, that means the starting value. So this is the starting value. 1/2 is just because it's half-lives. And then T is how much time. In our case that we just looked at, it was years. And N is the length of a half-life. And so what's important is that these two, T and N, have the same unit. So if half-life is in years, T has to be in years. If a half-life is in minutes, T has to be in minutes. That's really important that those have the same unit. Okay, so we're going to look at 2 more examples here using half-life. We looked at one where we're given like a finite amount of time and a starting value that was, a regular starting value. In example 2 here, it says, what percentage of carbon-14 will be remaining in a specimen after 10,000 years? So it's really similar to the previous example. How much is going to be remaining? That's going to be A. How much did we start with? Well, it doesn't tell us how much we started with. It just says what percent is going to be remaining. Well, we start with 100%, right? So we're just going to put 100 in for N sub 0. So we put 100 there, not because it's 100 grams, because it's 100%. It said what percent will be remaining. So our answer is going to give us a percent. And then times 1/2. And then time is 10,000. And the denominator is going to be 5,730. So this is what we're going to type into our calculator. And so you can just type all of this into your calculator just like this. So in an effort to save some time, I've got Desmos here, and I typed it in. I put 100 times 1/2 to the 10,000 divided by 5,730 power. So that exponent, that 10,000 over 5,730 is giving us how many half-lives? And so there's going to be about 29.8% remaining of this specimen, basically. So we'll head back here, and this was 29.8%. Had you put 1 instead of 100 in there, you would have gotten 0.298, and you would just convert that to a percent, and you're good to go. Okay, so those are pretty much the basic intro-level half-life problems. The third example is going to be a little bit more complicated, and in order to understand this one, you have to understand a little bit of higher-level math, like pre-calculus. So this is geared toward my pre-calculus students. It says a sample from a fossil contained 100 milligrams of carbon-14. It's estimated from the sample that it originally contained 300 milligrams of carbon-14. Approximately how old was this sample? So let's start filling in. What I'll do is I'll start out with just writing down the formula. A equals N sub 0 times 1/2 to the T over N power. So A is how much we started, or how much we ended with, and we ended with 100. So that's how much there is today. And it's estimated that it started with 300. So N sub 0 is going to be 300. 1/2 is just 1/2. That doesn't change. And so when the next thing is, it says approximately how old is the sample? Well, the N is still 5,730. So it's going to be T divided by 5,730. So I'm using carbon-14 for all these examples. Not every half-life uses carbon-14. The number 5,730 will change every time. Okay, so here's where I said you need to understand some pre-calculus or some advanced algebra. We're going to divide both sides by 300, because really what we want to do is we want to solve for T. And this becomes 1/3 equals 1/2 to that power, t over 5730. So, in order to solve if t or x or any letter is in the exponent, you have to take the log of both sides. So this is where our calculators are going to come in handy. So we're going to end up with the log of 1/3 equals the log of 1/2 to the t, that's an ugly t, over 5730. Okay, we're going to scroll down here. When I do that, the trick with logs is if you take the log of both sides, now this exponent can come out in front, and we can rewrite this as log of 1/3 equals t over 5730 times log of 1/2. Okay, and then if I want to solve for t, I can divide both sides by log of 1/2. And it's tempting to want to cancel out the logs here, but that doesn't work like that. You don't, it's kind of, think of it kind of like square rooting. If you square root 1/3 over square root 1/2, you don't just cancel out the square roots and say it's 1/3 over 1/2. It doesn't work like that. So we're going to keep those logs. Log is an operator. So then we're going to come over here, and I'll finish it out over here. We've got log of 1/3 divided by log of 1/2 equals t divided by 5730. So to solve for t, I'm going to multiply both sides by 5730, and then it's a calculator situation. 5730, it looks like 5736. Let's fix that. 5730 times log of 1/3 over log of 1/2. That's our time. So now I just need to grab my calculator and figure out what that is. So let's run to Desmos. We'll do that. Get rid of that stuff. All right, so 5730 times, and then I'll go over here and grab the log of 1/3. And I'll close my parentheses. Divided by log of 1/2. And I'll save some time by doing 0.5. And so the answer is 9,081.8. So about 9,082 years old is that specimen. 9,082. So it asked us approximately how old is that? It's around 9,082. Now obviously we could have made a mistake or guessed wrong with the initial, but it's around 9,000 years old. All right, so that's a more advanced half-life problem where you have to take the log of both sides to cancel out and solve for an exponent. The previous two examples were pretty much straightforward if they gave you the time. So that's half-life in a nutshell.